So today we will talk about attribute control charts. If you remember, attribute control charts means that the output data or the output of measurement is represented by discrete data. So basically it's either conforming, non-conforming, good or bad part, okay or not okay, or it counts the number of non-conformities. For binary data, which is conforming, non-conforming, we use two control charts, P and NP. And for counting the number of non-conformities, we use C and U control chart. And in this lecture, we cover P and NP, and C. In this lecture and the next lecture, we cover P and NP and C control chart. So non-conforming items, so let's say we have a sample of n parts, and then we count the number of bad part or non-conforming units. We call this as, we denote it by D, as you can see, is the summation of xj in the sample, and x1 to xn is either 0 or 1. So if I want to count the number of non-conforming items, then I have summation of these 0 and 1s. This is the number of non-conforming items. We also have fraction non-conforming for a sample, which is the ratio of non-conforming units to the sample size. So it's defined by D divided by N. D is the number of non-conforming units in the sample that you have, and N is the sample size. So it's a number between 0 and 1. So if we define a control chart based on D, this control chart called NP chart, and if we define a control chart based on P hat, which is the fraction non-conforming, this control chart is called P chart. So here's the important thing. We know that the distribution of D is binomial because it's the number of success in n Bernoulli trials, or the number of bad parts in a sample with size n. Now, what is the distribution of, I know distribution of D, but what is the distribution of D divided by n? This one can be approximated using central limit theorem, and can approximate it by a normal distribution using central limit theorem, where mean is P and the variance is P times 1 minus P divided by N. So what is P here is the fraction non-conforming of the process. So P hat is the fraction non-conforming of a sample. P is a fraction non-conforming of the process. So these two are different. As I said, it can be estimated by a normal distribution, approximated by a normal distribution using central limit theorem if n is large. And when we say n is large, it should be at least 100 or more than 100 in order to able to use basically central limit theorem and normality approximation. If p is close to half, then we need less sample size. But in reality, especially when we are talking about Six Sigma projects, then the fraction non-conforming is a small value. That's why the smaller value that you have for P, which is fraction non-conforming of the process, you need the larger number of sample you should have in order to get a normal distribution. And P0 here, just some notation, is the in control fraction non-conforming. If P0 is given, then we can easily find basically UCL and LCL for P chart. So because this is mean, this is variance, so mean plus minus K standard deviation is control limits. So that's P0, which is mean, plus K standard deviation, minus K standard deviation. And if LCL happens to be negative number, and if your sample size is small, that could happen. If sample size is large, you can basically avoid this problem. But if it happens to be a negative number, we set LCL equal to 0, because we know that it doesn't make sense to have negative number of non-conforming items. And as I said, if P is closer to 0.5, a smaller sample size is needed for central limit theorem to be true. What if in practice P is not known, so we don't have P0? What should we do? We should do phase 1, similar to what we had in X bar and R chart, in order to estimate P. So what we do, we first collect M samples, 25 to 30. So we have a sample, 1 to 25, and based on that we can calculate DI of each sample, which is the number of bad parts in the sample of, let's say each sample n is 100. At each time we inspect 100 parts, and the corresponding DI would be the number of bad parts. So let's say it's 5 here, 10 here, 15 here. Then what we do, we calculate P hat I, which is DI divided by N. In this case is 0.05 because N is basically 100, or 0.1 for this, or 0.15 for this guy. We calculate that, then based on this, we can estimate the P or P0, which is the fraction non-conforming of the process. How? Using this equation, as you can see, is the average of all these PIs that I have. And we denote this average or estimate by P bar. Now, if I know this P bar, I can easily find UCL and LCL. As you can see, this is same equations. I'm just replacing P0 by P bar, which is the estimate of P. So UCL, LCL, and CL. So this is important. If a point is plotted on the control limit, then we assume that it's a out of control point, unless LCL is negative. And when LCL is negative and you move it back to 0, if a point is plotted on 0, then it's not out of control. This is phase 1. So if the point is outside the limit, we should find the root cause, and we should try to take the corrective action and remove the point and do the calculation. So for P-chart, there are 2 types of assignable cause. Let's say we have this control chart, and this is P hat. So what we plot here is P hat values. So let's say these are the P hat values for each sample. I can see something like this, which means the quality of the process changes because the P increases. So I find the root cause, whatever it is, I try to do corrective action and basically make the process stable and remove these observations from basically the data, the sample that I have, and recalculate all the LCL and UCL. Another case would be the case that you have in control data, but suddenly you see out of control from the LCL side. What does it imply? From the LCL side means P hat decreases, okay, so or process fraction non-conforming decreases. In terms of quality, this is a good thing because now you are producing lesser number of bad parts. So what should we do? We should find the root cause, that's definitely, but we should not remove the root cause because it's a good assignable cause. We should find the root cause and make it permanent in the system. After that, we remove all we had before, and we redo phase 1 again. For P and C control chart, P and C control chart, if you see some observation or out of control from LCL side, it's a good assignable cause. We need to basically make it permanent into the system. Now, here is one example. Let's say we are interested in monitoring packaging process for frozen orange juice concentration. And what we do, we collect 30 samples. So M is 30. And each sample includes 50 observations. And here is basically the observation. This is 1 to 30. And the second column shows how the number of non-conforming packages out of these 50, so it's 12, 15, and so on and so forth. And the third one is P hat I, which is DI, the number of non-conforming divided by N, in this case is 50. So I have all these fractions here. So what I can do, I can take the average of all these numbers, and I get a good estimate for process fraction non-conforming, process percentage of non-conforming items. Based on that, I can easily find UCL, LCL, and CL, which is the center line. That's P bar. So I just plug in these numbers here. N is 50 and P bar is this guy. I can find UCL and LCL. This is LCL and UCL. We call it trial because we are in phase 1. We plot them and we will find that 2 points are out of limit. So what should we do? We need to find the root cause. We need to try to remove the assignable cause and remove these points from calculations. So as you can see, here is the numbers that we have. So one is because of new material, one is because of new operator. We try to train operator and we try to make sure that the new material, the problem that we had with new material doesn't happen again. Here, we remove these 2 points, okay, from calculations. We calculate P bar again, and based on P bar, we calculate LCL and UCL. So here are revised UCL and LCL based on revised P bar. So P bar is now summation of all these p hat I, except for these two numbers, divided by 28, because we removed two samples. Then we have LCL and UCL, and as you can see, there is no new point outside the limit. We remove these 2 points, except for one. This is the point that we have outside the limit. We try to find any root cause for that, but there is no root cause. And if something like this happens, only 1 point, then we can say this is type 1 error of control chart, and we can just ignore it. So in this case, I can say this LCL and UCL are baseline or finalized, and then I can use it for phase 2. Now let's see how we can perform phase 2. As I said, phase 2 is online monitoring and 1 point at a time. So this is revised LCL and UCL obtained from phase 1. This is the control limit estimation, which is the phase 1 again. From 31, I have phase 2. And it's one sample at a time. So 31, I collect a sample of 50 frozen orange concentration. 9 of them has problem, which is 18%, and I plot this 18% here. Then I start like plotting them, and one by one, and over time I see that p values or p hat I start decreasing. At some point is below LCL, but overall you can see based on the 8 consecutive points below LCL, I can say there is something, the process is out of control. But since p decreased, so it's a good out of control or a good assignable cause. What should I do? I need to find basically the reason. And the reason is machine adjustment. So we adjusted machine somewhere here, and it helped improve the quality of part. So what should we do? We should get rid of all data that we had. We need to use this data and redo phase 1. And that's what we did in this example. So as you can see, this is before and after machine adjustment. I have this data. I need to use this data, recalculate p bar, which is summation of pi divided by m, which is summation of these numbers divided by the number of samples that I have. And this is the new CL, this is new UCL, and LCL in this case is negative, which we make it 0, as you can see. So this is UCL based on new p bar. So new control limit calculated. And as you can see, there is nothing out of control here. Seems everything is fine. So these two limits that we calculated here is now baseline for phase 2, another phase 2 that we have. Then we continue with monitoring the process. As you can see, from 55 is based on new control limits that we have, and one at a time. These are the control limits we had. We already seen it in the previous slide, and here is the control chart plot. From 55, this is one at a time point, it's phase 2, and process is in control. So now you can see we have started with this process. Then we found an assignable cause, which is a good assignable cause, was machine adjustment. We removed that part. We found another trial and baseline control limit, and we continued with phase 2, and everything is looking fine, and the process is in control. With that, we finish this lesson. In the next lesson, we will learn more about NP chart as well as C charts. Thank you.